Here we want to talk about the design of a living machine. So this is just a guide to agentic negentropic control. And so what is the framework really about? Well, imagine that you're trying to build a blueprint for an intelligent agent. Now that agent could be a bacterium surviving in a hostile environment. That agent could be a robot navigating a warehouse. It could be a trader making decisions in financial markets. It could even represent a human being trying to get through a difficult week, It's agentic negentropic control. How does an agent maintain its state of order in a system that's fluxing and experiencing stochastic interruptions? Now, this framework that we're describing here it's essentially a unified mathematical language for describing how any agent can stay organized and make smart decisions and spend its energy wisely, how it can remember its past, how it can imagine its future, how it can simply remain stable without falling apart. Okay, so the central obsession of this framework is something called negentropy. It is an obsession, the tendency of a living or intelligent system to resist disorder, to maintain its internal organization against the constant pressure of a chaotic universe. The world is dissipative. The agent is trying to resist dissipation. So everything in this framework, it serves that one master goal, that one negentropic goal. So we need to talk about the bundle. This is the stage on which everything happens. So let me describe a fiber bundle. Think of a universe of possible situations. The framework begins by describing what mathematicians call a fiber bundle. But you can think of it as just a sophisticated filing cabinet. So imagine that every possible configuration in the world, every temperature, every position, every state of energy, everything, it gets at one drawer in this massive cabinet. Now, the cabinet itself is labeled by a set of parameters that describe the type of system that you're dealing with. Say that it's a warm system, or is it a cold system? Say it's a fast system or a slow system, a stiff spring or a loose spring. Each drawer contains all the possible states that system can be in, given its type. Now, the bundle is just the whole cabinet together with all of its drawers, all of its possibilities, okay? When you talk about a fiber bundle, that's what they're talking about. Now, why does this matter? Because this means that the framework can describe families of agents all at the same time. It's simultaneous. It's not just one fixed agent. So a practical example, what about a pharmaceutical company that's running clinical trials? It doesn't care about just one patient, you see. It cares about the whole population of patients, all of them with varying physiologies, and so the bundle captures the entire population at once. And the framework's tools apply to all of these, all the population coherently. What about a robotics engineer? He's building an acceptable machine. He will benefit similarly from a fiber bundle approach, such that rather than designing one robot for one task, the bundle lets you design principles that work across an entire family of tasks or an entire group of environments. So, fiber bundles. Now, the energy metric, we're also included in here. We need to apply that such that not all directions are created equal. Let's unpack that. So inside each drawer of the filing cabinet, distances are not measured with a basic ruler. Instead, there's a special weighted ruler called an energy metric, which says that some directions in the space of possible states cost more energy to move along than other directions. So think of it like you're hiking in a terrain where some paths are uphill and some paths are downhill. What the metric is telling us, the energy metric, is telling us the shape of the landscape. And it's enormously important because it means that the framework is always physically honest. It never pretends that some high-energy environment is cheap, and it never ignores the fact that fighting gravity is going to cost you something. So the energy metric is critical to our negentropic process here. But in practical terms, this is how a robot's controller knows that spinning a heavy arm is going to require more effort than nudging a light finger will. And in biological terms, this is why a muscle cell doesn't waste adenosine triphosphate. This is the body's energy currency. your muscle doesn't waste its ATP on movements that it doesn't need to make. The energy metric is the framework's way of encoding physical reality directly into the mathematics of decision making. That's the fiber bundle, all the possible situations, and the energy metric, which says not all of these situations are equally negentropic or energy efficient. Okay, part 2. Let's talk about the Port-Hamiltonian dynamics. This is looking at physics as a flow of energy through ports. Port is a connection point, so the Hamiltonian is the energy flow. So what Port-Hamiltonian means basically is system as a network of energy exchanges. So one of the most powerful physical ideas in this framework is the concept of Port-Hamiltonian dynamics. The word Hamiltonian, it comes from the 19th century physicist, and it just means the total energy of a system. Then the word port, of course, is borrowed from electrical engineering, and it means a place where energy can flow in or out. That would be like a USB port on your laptop, or the mouth of a living creature is also a port. But anyway, together, the Port-Hamiltonian dynamics describes a system as a network of interconnected energy reservoirs and also of exchange channels, each of them obeying strict conservation laws. The equations in this framework say that at any moment, the agent's physical state is changing for 3 reasons at the same time. The first reason, there is an internal flow of energy that is perfectly reversible, like energy sloshing back and forth like a pendulum without any loss. Okay, secondly, there is a dissipative flow that represents genuine energy loss. That could be friction, it could be waste heat, it could be metabolic burning. Anyway, that's the second part, is dissipation. And dissipation always costs something. It can never be recovered, so it's not reversible. Then the third state is there's a control input. This is an intentional act, and it injects or extracts energy through a designator port. And so this structure, it's a smart approach because it guarantees certain physical laws are never violated, no matter how complicated the system becomes. You see, so now we can begin assembling models and assembling systems like Legos and not have to worry about whether or not the output from one model is going to result in nonsense if it's used in another model. So a practical application of this idea would be found in modern power electronics, where engineers, they design converters that move energy between batteries, between motors, between grids. So the Port-Hamiltonian framework is going to ensure that no energy is accidentally created or accidentally destroyed in the design equations. Think of modeling a cardiac muscle cells, where the port structure captures how chemical energy from ATP is converted to mechanical work in the heart's contraction cycle, with losses due to heat and losses due to internal friction accounted for automatically in the system. So part 1, remember, that's the bundle, the energy metric there. Part 2 is the Port-Hamiltonian, and still continuing with the Port-Hamiltonian, we have to talk about Stratonovich noise. This is really honoring the geometry of randomness, so let's unpack this. The framework adds randomness to the dynamics using something called the Stratonovich form rather than the more common Ito form. This is a technical choice that sounds arcane, it sounds kind of off-center, but it does have an important physical meaning, because Stratonovich noise respects the geometry of the state space, meaning that if you apply a coordinated transform to your variables, the random fluctuations will transform sensibly along with them. So it's as if the noise knows what shape the landscape is, and the noise will jiggle the system in a way that is geometrically coherent rather than just naively adding some vibration without regard to the direction of the system. So think of it in this way. If you're describing the orientation of a spinning top, then Stratonovich noise ensures that the random buffeting from air currents, it still leaves the top spinning on a sphere of orientations instead of just accidentally launching it into some mathematically absurd state outside of that sphere. So there is a state outside of what's possible for that system, and there is a state inside of what's possible. Ito may accidentally launch it into a state that's outside of what's possible. But Stratinovich won't do that. That's the point. So think of an engineer who's designing a satellite's attitude control system. So this means the noise model for disturbance torques stays geometrically consistent with the constraint that the satellite must always have a well-defined orientation. That's the constraint. What about in a biological system? For a biologist modeling the random switching of gene expression networks, for example, Stratinovich form ensures these stochastic fluctuations are going to always respect the underlying biochemical geometry. So we're using Stratinovich noise in our Port Hamiltonian dynamics instead of Ito form. Okay, let's talk about part 3, which is the agent itself, and basically 3 interacting layers of self. First of all, the physical state, the body. So the agent begins with the most concrete layer, the physical state, which is simply the actual measurable configuration of the system at any moment in time. The position of the robot's arm, the voltage across a neuron's membrane, the concentration of a hormone in the bloodstream. This layer is going to obey that Port Hamiltonian, those equations that we've described above, and the layer is also subject to all the physical constraints of energy conservation and dissipation. It is the body of the agent, and everything else the agent does is ultimately expressed through this body, and it draws on the energy budget of this body. So a practical example, think of a drone in flight. It's going to have a physical state consisting of A, its position, B, its velocity, C, its rotation speed of all 4 of its rotors. But anyway, every decision the drone makes, every control signal sent to those rotors, every decision is ultimately an action on this physical state. The framework insists that those actions must be costed in real energy terms, such that spinning a rotor faster is going to require electrical power drawn from the battery, and the battery has a finite capacity. And so this is the energetic honesty that the framework enforces. The second layer would be the information state, or the mind. Remember, the first was the physical state of the body. The second is information state, the mind. Now this second layer, it's what the framework calls the information state, or internal belief representation. This is the agent's internal model of the world. Its best current guess about what is true, about what has happened, and about what's probably going to happen next. And crucially, this internal model also is treated as a physical system with its own energy dynamics, its own dissipation, and its own ports for information exchange. The framework explicitly recognized that thinking costs energy in just the same way that moving costs energy. So this is not merely a philosophical statement. This is a physical fact grounded in thermodynamics. Every time a neuron fires in our brains, that neuron is consuming glucose. Every time a computer processes information, it's drawing on some current. Now, the Landauer principle in physics, it establishes that even the erasure of one single bit of information is going to require the dissipation of a tiny but non-zero amount of heat. A positive amount of heat must be dissipated for any information erasure. Now, by modeling the information state with its own Port Hamiltonian dynamics, our framework incorporates the physical cost of cognition directly into the optimization problem at the root, at the core. So a practical application then might be in designing energy-efficient artificial intelligence for edge devices like hearing aids or insulin pumps or something. The information state dynamics is going to provide a rigorous way to trade off the quality of the internal belief updates against the battery life that's consumed in performing those updates. Okay, the third layer is the memory process. This is the history which actually shapes the present. So remember, we have the physical state as layer 1, the information state, layer 2, and the memory process, which is layer 3. And here the framework makes a particularly sophisticated move, right? It's going to represent memory not as a simple list of past events, not as a static record. Memory is a function that's defined over a window of past time, living in a mathematical space called a Hilbert space of histories. A Hilbert space of histories. What does this mean? Well, it means in practice that the agent's memory is a continuous, weighted record of its past experiences, where recent events might be weighted more heavily than distant events, or where certain patterns of experience are stored more faithfully than other patterns, depending on their relevance. So the biological analog of this is actually striking, because human memory is not a video recorder. It doesn't just play back discrete frames with equal fidelity. Human memory is a reconstruction which is weighted. It's a context-sensitive process where emotionally significant or frequently rehearsed events are recalled more vividly and influence present behavior more strongly. So our framework captures exactly this kind of a graded and continuous influence of history on the present decision-making of the agent. So in engineering, the analogous concept, it appears in recurrent neural networks and echo state machines, where a reservoir of recurrent connections maintains a fading memory of past inputs that shapes current outputs. This is a technique used in time series forecasting, in speech recognition, and adaptive control of systems with long-range temporal dependencies, like traffic flow or like climate. So the physical state layer, that's the body. The information state layer, that's the mind. And then the memory process, that's the history that shapes the present, the Hilbert space of histories. Okay, part 4, the operational present. We're just saying that time has 3 directions here, the operational present. So this 3-track view of time, past, now, and the imagined future. Okay, one of the most conceptually rich ideas in this framework is the explicit decomposition of time into 3 tracks, 3 coordinated tracks that are anchored at what is called the operational present. And this present is not just a mathematical point. This is the moment of actual sensory contact with the world. When an agent receives a measurement through its observation channel, that's the operational present. Now behind that present stretches the past memory track, the continuous record of what the agent has actually experienced. But ahead of the present stretches what the framework calls the counterfactual future track. Not what will happen, but what could happen under different possible action sequences that the agent is mentally simulating. Okay, so this 3-track structure formalizes something that psychologists and cognitive scientists have long recognized as central to intelligent behavior. It's the ability to simultaneously hold a record of the past, to engage with the present, and to simulate possible futures. Animals that cannot do this, they can only react to immediate stimuli. And so they're severely limited in the complexity of goals that they can pursue. Humans and other cognitively sophisticated animals are distinguished precisely by their capacity to hold long past records and to simulate deeply branching trees of possible futures. And so Agentic Negentropic Dynamics framework, it gives this capacity a precise mathematical form that can be implemented in artificial systems. Now, a practical application of the model predictive control is engineering, where a controller maintains a model of recent history of the system, then it observes the current state of the system, and then it rolls out many possible future trajectories under different control inputs in order to choose the best trajectory. Now, this is exactly the 3-track structure that's described here. And so this approach is used already in autonomous vehicle driving, building climate control, chemical process optimization. Let's talk about the observation channel, how the agent touches the world. The measurement equation in this framework is we're calling it the observational channel. It deserves special attention because it describes the fact that the agent never has direct, perfect access to its own physical state. Instead, it's receiving a noisy, partial projection of that state through a measurement operator that acts like a camera with limited resolution and a fuzzy lens. The noise term represents all the sources of measurement uncertainty. It could be sensor imprecision, it could be environmental interference, finite sample rates, randomized initial conditions, anything could be a noise source. Now, this is universally true of any real sensing system. Thermometer is going to give a noisy estimate of temperature. A stock price is a noisy signal about the underlying value of a company. An fMRI scan, it's a blurry indirect measurement of neural activity. So this framework's explicit treatment of this measurement imperfection, it means that every inference the agent makes about its own state, and of course thereafter every decision that it makes, it has to account for this fundamental epistemic limitation. The environment is always going to have more information than the agent has channel capacity to read fully. And so there's always some degree of guessing, always some degree of gambling involved in, or uncertainty, right, involved in any information that it has or decision that it makes. So in practice, this is the foundation of Kalman filtering and Bayesian state estimation. These tools that are used ubiquitously in navigation and medical monitoring and financial modeling and in robotics, and of course it has to be acknowledged here. So part 5, we'll talk about counterfactual reasoning. So this is the actual signature of true agency. And what is counterfactual divergence? What does it really mean? So agentic negentropic dynamics defines this most essential signature of genuine agency as something we're calling, of course, counterfactual divergence. So here's the intuition. Imagine you can run 2 thought experiments, and in the first you just do nothing. You just let events unfold as they would. You just let events unfold as they would without any intervention. Now in the second thought experiment, you take a specific action and you imagine how events would unfold differently. Counterfactual divergence is the precise measure of how different these 2 futures would be. A high divergence means your action makes a big difference to what happens, and a low divergence means that your action barely matters. Okay, what this framework does, we're using a measure from information theory called the Kullback-Leibler divergence. This is a way of measuring how different 2 probability distributions are, and we're using that divergence to quantify the difference in possible futures. The deeper meaning is actually profound. It is that an agent is only genuinely agentic if it can make a difference, and moreover, if it can compute how to make a difference, and if it has the resources to act on that computation. Okay, so a thermostat that only oscillates between 2 states, regardless of your input, is not truly agentic. But a chess grandmaster who can choose moves that radically alter the landscape of the game is agentic, right? The practical application of counterfactual reasoning, there's many applications, but in medical decision making, for example, a doctor asking, what would happen to this patient if I prescribed this drug versus that drug? That's computing a counterfactual divergence intuitively. In causal machine learning, though, counterfactual inference is used to estimate treatment effects in randomized trials, recommended personal interventions, and audit AI systems for fairness by asking what would have happened to a person with different characteristics. So, again, counterfactual divergence. Now, we have to also discuss why the divergence has to be achievable within budget. A crucial constraint on this framework is that the counterfactual divergence only counts as real agency if the agent can actually achieve it within its available resources. Now, you might be able to imagine a sequence of actions that would radically transform your future, but if carrying out those actions would require more energy than your body contains or more information processing than your brain can handle, then that divergence is not realistic. It's just hypothetical. It's not operationally real. So we don't count those. So we have to enforce this constraint explicitly by requiring that the divergence can be achievable within the information budget and within the metabolic budget simultaneously. Now this captures a profound biological reality, actually, such that every living organism operates under a tight metabolic constraints, and those constraints, they limit the complexity and the reach of its cognition and of its action. So, for example, a fruit fly can perform remarkably sophisticated sensorimotor computations for its size, but its total neural energy budget is orders of magnitude smaller than a human's. And this limits the temporal and spatial reach of its counterfactual planning. So our framework, our budget constraints are not just bookkeeping. They're a mathematical expression of the physical limits that define the niche within which any real agent can operate. And that's critical. It's a crucial constraint. Let's talk about part 6 now, which is the information and metabolic budgets, or the thermodynamics of thought and action. Now, the information budget. Okay, thinking has a price tag. The information budget in the framework, it measures how much it costs the agent to maintain its internal model of the world at a given level of accuracy. So a key concept is mutual information rate. This is just roughly how fast the agent is gaining useful information about its environment from its measurements. Now, maintaining a more accurate, a high-resolution internal model is going to require a higher rate of information processing, and the framework assigns this a direct energetic cost through a scaling constant. Now, this is the mathematical formalization of a principle that cognitive scientists call bounded rationality. Real agents cannot afford to be perfectly rational in an economic sense, because perfectly rational would require infinite information processing. You don't have that. So instead, agents must make good enough decisions given a finite cognitive budget. So A&D framework, it makes this trade-off precise and optimizable, such that given a fixed information processing budget, what is the best internal model to maintain, and what decisions does that model support? So it's a filter, basically, a filter based on your budget. In engineering, this will appear in the design of compressed sensing systems, where a sensor deliberately subsamples a signal and it uses clever reconstruction algorithms to recover the important features so that it's just paying a small information processing cost to avoid the larger cost of full sampling. In machine learning, information bottleneck method, these methods use exactly this kind of information budgeting so that, when they design neural network layers such that they retain only the most task-relevant features in their inputs, and they discard the rest, and thereby they reduce their computational cost and they improve generalization that way. Okay, so when we're talking about the thermodynamics of thought and action, well, we talked about the thermodynamic budget of thought, but we also have a budget for action. And action, of course, has a price tag too, a larger price tag. Action does. The metabolic budget is going to track two kinds of energetic costs. The first is the instantaneous cost of the actions themselves. So that's just how much work the agent's actuators have to do to execute a given control input. A robot lifting a heavy box is going to pay this cost in motor torques, joint forces, stuff like that. And a bacteria that's swimming against a chemical gradient, it's going to pay the cost with its flagellar rotation, driven by proton gradients across its membrane. There is a cost to pay in both cases. Now, that's the first kind of cost. The second kind of cost is what the framework calls irreversible housekeeping costs. And that's the energy that has to be spent simply to maintain the agent's organization, regardless of what action it takes. It's to hold its own against the void. Now, this is the biological concept of basal metabolic rate. So even when you're sleeping perfectly still, your body is still burning calories just to maintain your body temperature, to keep your neurons firing at their resting potential, to repair any kind of damaged proteins, to sustain 1,000 of other processes that keep you alive and organized, right? So the A&D framework's explicit inclusion of housekeeping costs reflects the deep biological truth that staying organized in a disorganized universe is not free. It requires a continuous expenditure of metabolic energy to do so. Well, here's a practical application. In the design of implantable medical devices like pacemakers or neural prosthetics or something, the distinction between action costs and housekeeping costs is going to be critical for battery life estimations. The device has to spend energy both on its actual therapeutic actions and on simply maintaining its computational and sensing systems in a ready state. And A&D framework provides a principled way to allocate the finite battery budget across these two competing demands. All right, let's talk about part 7, the variational objective. So how the agent decides what to do. This is a Lagrangian. It's a three-way tug of war. Let's talk about this. The variational objective is the agent's master decision-making criterion, the single mathematical expression that captures everything the agent is trying to achieve, weighted by how much it cares about each consideration. It combines three terms in kind of a competition or a tug of war. The first term is the physical energy cost. These are actions that require a lot of energy from the physical system. Those actions are penalized. Now, the second term is the information processing cost. It says that maintaining a very accurate internal model or transmitting a lot of information through control channels is penalized. The third term is the task or the reward cost, such that failing to achieve the agentic goal, like staying alive and reaching a target or maximizing its profit, failure is penalized. Now, the relative weight given to each of these three terms, represented by the parameters alpha and rho in the framework, the relative weight determines the agent's character. An agent that weights energy cost very heavily will be conservative. It's going to prefer low power actions even at the cost of task performance. But an agent that weighs task performance very heavily will spend energy lavishly. But an agent that weights information cost heavily will prefer to act under uncertainty rather than to invest in reducing that uncertainty first. And now, real biological organisms have these specific weightings of these three terms that are appropriate to their ecological niches, like a predator is capable of short bursts of high-speed pursuit, but it really can't sustain high continuous expenditures. That has an implicitly high energy cost weighting in its behavioral repertoire, for example. Okay, what is the KL regularizer? It's saying don't diverge more than is necessary. So on the top of the three-way Lagrangian, this framework adds a penalty term proportional to the counterfactual divergence itself. Now that might seem paradoxical, because earlier we said that the counterfactual divergence is the signature of genuine agency, but now we're penalizing it. The resolution is that this penalty enforces economy of agency. Like, the agent should not make the future more difficult from the baseline than is necessary to achieve its goals. So gratuitous divergence, this is action for action's sake, change for change's sake. That's wasteful and is potentially destabilizing. So this has a profound biological correlate in the principle of least action and the concept of homeostasis. Because a healthy organism does not constantly push its physiology to extremes. Instead, it maintains a stable internal environment, and it only departs from that stability when the goal requires it. So the KL regularizer is the mathematical enforcement of this conservative wisdom, and it ensures that the agent's interventions are purposeful and that they're proportionate rather than extravagant and disruptive. So in reinforcement learning, this idea appears as KL regularized or entropy regularized policy optimization, where the learning algorithm is penalized for choosing action distributions that deviate too far from a safe reference policy. And this technique is used in training large language models, robot locomotion controllers, financial trading algorithms, and it's used to prevent catastrophic or irreversible actions. In part 8, we have to talk about the memory dynamics, how the past shapes the future without being present. So let's discuss this from the perspective of the reservoir equation, that memory has a leaky tank. The framework describes memory evolution using what engineers call this reservoir equation. It's an equation that says the memory state at any moment is driven by new observations flowing in while simultaneously decaying due to a forgetting or dissipation process that's represented by the decay rate matrix. And so these is pruned memories in order to keep the size of the memory small enough to be computation friendly. Now, the analogy is a leaky tank, where water pours in from a tap representing new experiences, but simultaneously that water leaks out through holes, which represents forgetting. And the current water level represents the current state of the memory about past events. Now, the sophistication here lies in the fact that different frequencies of experience decay at different rates. Some memories fade quickly, others persist for a long time. All of this has to be captured by making the decay rate a function of the time scale within the memory window. This is directly analogous to the multi-timescale memory consolidation process we have in our biological brains, where short-term working memory decays in seconds, episodic memory consolidates over hours through sleep-dependent processes, and semantic memory can persist for a lifetime. In engineering, reservoir computing and echo-state networks explore exactly this principle to build powerful sequence processing systems without the computational expense of training all the parameters. The reservoir, which is a fixed, random, recurrent network, it maintains a rich fading memory of past inputs, and only the readout layer is trained. This approach has been applied successfully to time series predictions in chaotic systems, to speech recognition, and also to controlling robotic arms with complex dynamics. Still under memory dynamics, we want to talk about the Volterra kernel. This is a long-tail memory in a formula. So for the generation of predicted future trajectories from memory, the framework invokes Volterra series representations. This is a mathematical technique for expressing how the output of a nonlinear system at any moment depends on a weighted sum of all the past inputs, with weights that decrease as the past grows more distant, so decaying memory. This is sometimes called a long-tail memory representation because the influence of the past decays gradually rather than cutting off sharply. The biological analog of this is the way a jazz musician improvises. The current melodic phrase is shaped not just by the last note they played, but by the entire arc of the piece so far, by the harmonic progressions they've heard years ago during practice, and also by the model conventions of the jazz tradition that they've internalized over the decades and stuff. All of these influences, they persist as weighted contributions to that present moment. They're improvising in the present moment, but the more recent and the more salient influences are going to be weighted more heavily. And so the Volterra framework, it gives us a precise mathematical form that can be fitted to data, and it can be used for prediction. In practical signal processing, Volterra series are used to model and to compensate for nonlinear distortion in audio amplifiers, radio frequency power amplifiers, biological neural circuit. The identification of Volterra kernels from input and output data is a standard technique in nonlinear systems identification, with applications ranging from hearing aid design to the modeling of visual cortex responses in neuroscience. Now, the last section under memory dynamics is just the Bayes consistent memory updates, which is learning without hallucinating. So, when new observations arrive, the framework updates the memory state using a Bayes consistent assimilation rule, a procedure that combines the new evidence with the existing memory in a mathematically optimal way that never violates the laws of probability. The critical constraint is that this update must not cause the total energy stored in the memory to explode. The energy norm of the memory state after the update must not exceed the energy norm before the update by more than a small accountable bookkeeping term. This is going to prevent the system from hallucinating or from generating internally consistent but physically impossible memories that would corrupt future decision making. The biological analogy of this is the consolidation process in memory. When you learn new information, your brain doesn't simply overwrite the old memories or randomly scramble existing knowledge. Instead, it integrates that new information with existing schema, maintaining internal consistency. And so our framework's energy-bounded memory update is the mathematical counterpart of this consolidation constraint. Now, in engineering, the analogous principles appear in Kalman filtering, particle filtering. This is where measurement updates are bounded to prevent filter divergence, or a pathological condition where the filter's internal model drifts arbitrarily far from reality. Okay, part 9, symmetry detection and exploitation. So this is a way that we can work smarter instead of working harder. What symmetry means for an agent here? A symmetry in this framework's sense is a transformation of the agent's state that it leaves the basic dynamics unchanged. if you can rotate a perfectly symmetrical crystal by 60 degrees and it still looks identical, that means that rotation by 60 degrees is a symmetry of that crystal. If a robot's task is equally hard, regardless of whether it starts facing north or south, then the task has rotational symmetry. Detecting and exploiting symmetries is enormously valuable from an energy perspective because it means that the agent doesn't need to separately learn or plan for each orientation. It only needs to solve the problem once for one representative configuration, and it applies the symmetry to get the answer for all the others. So it's a shortcut, a huge shortcut. Now, the framework provides a statistical test for detecting whether a proposed symmetry actually holds in the observed data, based on checking whether the measurements remain consistent when the symmetry transform is applied. This is essentially asking, okay, does the data look the same before and after I apply this transformation? If the answer is yes, the symmetry is real and it's exploitable. If the answer is no, then the symmetry is either broken by the environment or it's maladaptive in some way. Anyway, practical applications are they're immense. I mean, in physics-informed machine learning, enforcing known symmetries of the underlying physical laws into the architecture of the neural network can reduce the amount of training data needed by orders of magnitude, because the network doesn't have to separately learn what could be inferred from symmetry. In drug discovery, their molecular symmetry is used to reduce the computational cost of simulating drug-protein interactions. In robotics, exploiting bilateral symmetry allows a legged robot to transfer a gait learned on one side of its body to the other, and that, of course, it's going to dramatically accelerate its learning. Okay, what about symmetry breaking? Symmetry breaking is when the conformity is maladaptive, right? So sometimes the world is not symmetric, or sometimes the agent's task requires breaking a symmetry that the environment enforces. If that happens, our framework is going to address this explicitly with a symmetry breaking scaffold. It's a design control input that's intended to actively increase the symmetry of the system's trajectory in a useful direction. So the agent is deliberately going to push the system away from a symmetric equilibrium towards a more differentiated, informative, or task-adapted state. The biological analog is spontaneous symmetry breaking in development. So, for example, an embryo begins as a nearly symmetric ball of cells, but at a certain point, chemical gradients and mechanical instabilities break this symmetry to establish the head and the tail, the front and the back axes of the body plan. This symmetry breaking is not some failure, it's an essential controlled step towards a more complex and functional form. So the A&D framework's symmetry breaking scaffold is the engineering equivalent. It's a deliberate resource-costed intervention that moves the agent from a low information symmetric state to a high information asymmetric state that enables richer behavior. Think of it that way. In machine learning, symmetry breaking is used in the initialization of neural networks. If a weight starts at identical values, the network can't learn because all neurons compute the same function. So random initialization breaks the symmetry, and it allows different neurons to specialize. In part 10, we're talking about model reduction, where we want to keep only what matters. Model reduction is a weighted snapshot method where we're compressing a complex system down to its essence. And one of the most powerful data science techniques in this framework is the weighted snapshot method combined with randomized singular value decomposition. The idea is pretty straightforward. You collect a large number of snapshots of the system state at different times. You weight them according to the energy metrics so that high energy, physically important directions are going to count more. And then you find the smallest set of directions in the state space that captures those most important dynamics. This is dimensionality reduction informed by physics rather than just statistics. So think of it as finding the principal axes of a complex motion. If you film a flag waving in the wind and then you analyze all the pixel values across all the frames, most of the variation is captured by just a small number of dominant waving patterns. That's the fundamental mode, the first harmonic, and perhaps a few more. The flag's actual motion can be well approximated as a combination of these few patterns, even though in principle every pixel could be varying independently. But the weighted snapshot method finds the analogous dominant patterns in the agent state space, respecting the physical importance of each direction. Now, this technique is used extensively in computational fluid dynamics to reduce the cost of simulating airflow around an aircraft. It's used in climate modeling to identify the dominant modes of variability, like El Niño, and in structural engineering to find the critical vibration modes of bridges and buildings. And that randomized aspect of the single value decomposition, which uses random predictions to speed up the computation enormously, this is a modern data science innovation that makes this technique practical for very large systems. Now, when we're doing model reduction, we have to think about the truncation costs. We have to keep track of what we throw away. When you reduce a complex system to a smaller model, you inevitably throw away some of the information. These are the details that were captured by directions that you choose not to include. Okay? The framework insists on explicitly tracking this truncation cost as a trace of a matrix involving the noise covariance and the projection residual. In plain language, it just measures how much uncertainty is introduced into your predictions by having discarded part of the state space. So a high truncation cost means that your reduced model is missing some of the important dynamics and that your predictions are going to suffer. They're going to have large errors. But a low truncation cost means that your reduced model captures the essential behaviors well. So it's the error measure. The practical importance of this accounting, you can't really overstate that. I mean, engineers building reduced order models for real-time control applications like jet engine controllers, for example, they have to make decisions in milliseconds based on a model of a system with millions of degrees of freedom. So these control applications have to know how much error is introduced by their simplifications. The framework's truncation cost, it gives engineers a rigorous, physically meaningful measure of this error that can be incorporated directly into the controller's decision-making, which causes it to act more cautiously when the reduced model is known to be less reliable. Still on this model reduction part, we have to think about the identification covariance. How much do we really know? Separate from the truncation cost is the identification covariance. This is a measure of how uncertain the agent is about its own internal model parameters given the data that it's observed. This comes from a Bayesian perspective, like the agent maintains a probability distribution over possible values of the system's parameters, and the width of this distribution is the identification uncertainty. A tight distribution means the agent has a pretty good idea and it's pretty confident in its model, but a wide distribution means the data is too sparse or it's too noisy, and the model is probably poorly identified. So our framework combines these two sources of uncertainty, truncation and identification, combines them into a single total uncertainty budget that governs how cautiously the agent should act overall. High total uncertainty means the agent should be more conservative. It should prefer actions that are good across a wide range of possible models instead of actions that are brilliant under the best case model, but could be catastrophic if the model is wrong. So this is the mathematical formalization of everyday wisdom, just not putting all of your eggs in one basket, basically. So think about this in clinical medicine. This is exactly the reasoning that applies when a doctor has to choose a treatment under diagnostic uncertainty. The total uncertainty about the patient's condition, combining uncertainty about the diagnostics itself with uncertainty about how the patient's specific physiology is going to respond to the treatment. Anyway, the total uncertainty should influence how aggressive or how conservative the treatment plan is going to be. Robust decision-making under uncertainty is a core skill in medicine, also in finance, also in engineering, actually in everyday life whenever we're under a high-stakes situation. And Agentic Negentropic dynamics, it provides a quantitative foundation for this type of identification covariance. Part 11, the Pontryagin conditions. This is a recipe for optimal action. We have to talk about the augmented Hamiltonian. This is the master ledger of costs and benefits. So to find the optimal action sequence, the framework uses a technique from optimal control theory called the Pontryagin maximum principle. A central object is the augmented Hamiltonian. It's a master accounting ledger that at any moment tallies the instantaneous cost of the current state and action together with the future cost implied by the current trajectory, but weighted by joint processes that play the role of shadow prices. Each joint process answers the question, how much would my total future cost change if my current state were slightly different in this direction? So this is exactly the economist's notion of marginal value. Now the practical recipe is, then, at each moment, choose the action that minimizes the augmented Hamiltonian. This is a continuous time analog of dynamic programming. So instead of looking forward and imagining all possible futures, you just compute joint processes that summarize future consequences in a compact form, and then you make locally optimal decisions informed by those summaries. So the adjoint processes evolve backwards in time from the terminal condition, which is why they're sometimes called the co-state variables. Now this technique is the mathematical foundation of trajectory optimization in aerospace engineering, where it's used to compute fuel optimization trajectories for spacecraft maneuvers, but it's also the basis of backpropagation in neural networks, the algorithm that computes how to adjust each weight to reduce the output error, which is mathematically equivalent to computing adjoint processes for a discrete time optimal control problem. What about backward stochastic differential equations? Pricing the future under uncertainty. Again, still under this recipe for optimal action. Well, when the dynamics are stochastic, meaning that they include genuine randomness, then the adjoint equations become what mathematicians call backward stochastic differential equations, or BSDEs. These are equations that start from a condition at the future terminal time, and they solve backwards towards the present. The randomness in the forward dynamics requires a random component in the adjoint as well, representing the uncertainty about the future costs which were introduced by the stochasticity of the future states. So BSDEs were originally developed in mathematical finance for the pricing of derivatives as contingent claims, because a stock option's fair price today is going to depend on uncertain future stock prices, and that price must be computed by solving backwards from the option's terminal payoff through all possible future scenarios. Now, while we're using that, we're actually importing this financial mathematics directly into the theory of agentic control, recognizing that the problem of valuing a current action given an uncertain future consequences is formally identical to the problem of pricing that financial option. It's the same mathematical machinery, and so we can apply it to both cases. But in practice, BSDEs are solved numerically using Monte Carlo simulation of forward trajectories combined with the regression method to estimate the conditional expectations that appear in the backward equation. And this is computationally expensive, but it is feasible for moderate dimensional systems, and there is active research in machine learning methods for solving high-dimensional BSDEs as well, with computational efficiencies. Now, part 12 is our final part here. It's the Negentropic imperative. Why staying organized requires constant work. So Ito's energy balance, the laws of physics applied to hopes and plans. Our framework uses Ito's lemma. This is a fundamental result in the mathematics of stochastic processes. We use Ito's lemma to derive an exact energy balance equation for the agent's physical state. The equation says that the expected change in the system's energy over any time period can be decomposed into three conditions. First, the dissipative losses that always reduce energy, then the energy injected by control inputs, and then the correction term due to the randomness of the dynamics that has no classical analog really. The correction term, sometimes called the Ito correction, it's physically important because it represents the active energy that's injected into the system by random fluctuations. So think about Brownian motion, the juggling of pollen grains by water molecules there. It can, on average, push a particle away from a potential energy minimum, even when the deterministic force would pull it back. Now, in a noisy biological environment, then, random fluctuations are constantly adding energy to an organism's system, and the organism must work against this to maintain its organized state. So the Ito correction in the energy balance quantifies exactly this stochastic energy input. And the practical consequence is that the conditions for negentropic maintenance, for the agent to stay organized and not to dissolve into disorder, these conditions must account for this random energy input. a control policy that would be stabilizing in a deterministic situation, it would probably fail to be stabilizing in a noisy world because of that Ito correction. And that's why biological systems have redundant stabilizing mechanisms with generous safety margins. And that's why robust control engineering designs controllers that work well even under worst-case noise scenarios. So we've gone through a number of different points here, and I'm just going to recap. Part 1 was the bundle. That's the stage on which everything happens. Part 2 is the port Hamiltonian dynamics. That's looking at physics as a flow of energy through ports. Then part 3, we talked about the agent itself with the 3 interacting layers of self: the physical state, which is the body, the information state, which is the mind, and then the memory process, which is the history that shapes the present. And then, of course, there was part 4, which is the operational present itself, and such that time has 3 directions, and the operational present is where the agent interacts with the world right now. Then part 5 was counterfactual reasoning, which is the true signature of agency. Part 6, we talked about information and metabolic budgets, or the thermodynamics of both thought and action, and the budgets that must be applied in both cases. Part 7, we talked about the variational objective, how an agent decides what to do through the least action principle. And part 8, we talked about memory dynamics, how the past shapes the future without being the present, and the Volterra kernel, the base consistent memory updates, and all of that. Part 9, we talked about symmetry detection and exploitation, and how important that is for working smarter and not harder. Part 10, we talked about model reduction, and about keeping only what matters, but also about making sure that we do a proper accounting for that. And then finally, part 11, the Pontryagin conditions, the augmented Hamiltonian, and then the backwards stochastic differential equations, BSDEs. And then finally, Ito balance, the laws of physics applied to hopes and plans. So that was the negentropic imperative, and why we have to apply the Ito form in order to make sure that our systems will work not just in deterministic world, but also in a real stochastic world. So that little recap should help to recall some things to mind, and with that, we're going to wrap up this presentation.